All right, so let's now look at the charge effect. So a charge effect, if a species is charged, it's going to be more unstable than it would be if it was neutral. So when you see any charge, a positive or a negative, you should be thinking about how that affects the species and how it affects its acidity and basicity. So a positive charge is going to be attractive to electrons. And a positively charged species is going to want to give up its proton and regain electrons to regain its neutral charge more than a neutrally charged atom would be willing to give away a proton and become negatively charged. So, for example, if we're comparing H2O, which can also act as an acid, versus H3O plus, well, immediately I'm thinking H3O plus has that positive charge on it. It is unstable. It's going to want to give away its proton more readily than H2O. And how do I know that? Well, I think about what it would look like when H3O plus gave away its proton. If H3O plus gave away its proton, it would be H2O. It would be neutrally charged and a lot more stable. How about H2O? Well, if H2O gave away its proton, it would become OH minus. So it would actually be more unstable than it was before. So H3O plus is going to be more willing to give away that proton. So here is an example that we can look at to kind of illustrate this. So here we have H3O plus, and looking over here, we have H2O, and we just talked about that. H3O versus H2O plus. H3O plus is going to be the more acidic. And we can confirm that with looking up their pKa values. And remember, pKa is the inverse negative log of Ka. And so even if with Ka, you're looking at the larger the Ka, the stronger the acid. It's the reverse with pKa. The smaller the pKa, the stronger the acid. So you can see here there's a big difference between H3O plus and H2O. And we proved to ourselves here that H3O plus is more acidic than H2O. And same thing with NH3 and NH4 plus. Well, if I didn't know the pKa's, I would already be expecting NH4 plus to be the more acidic of the two. And we can see that's very true with the much lower 9.25 than 33. Okay, so another thing that we can do, though, is compare different acids, right? So instead of comparing H3O plus with H2O, we could compare H3O plus with NH4 plus. And how do we do that? Well, they both have a charge, so we can't use the charge effect to compare them. But what else? Well, what's different between them? The hydrogens are attached to nitrogen here, and here the hydrogens are attached to oxygen. So we can use the element effect. So here we're looking at across a row here, and we know from left to right it gets more electronegative and more acidic. So the oxygen, the H3O plus, is going to be more acidic than the hydrogens attached to the nitrogen. And we can go ahead and confirm that here. So we have a pKa of 9.25 for NH4 plus, and for H3O plus we have a pKa of negative 1.7. That's a pretty big difference. Okay, so that is, we just mixed the charge effect and the element effect. But what I would do is start familiarizing yourself with pKa values and look up online a pKa chart and then make one for yourself and try to get so familiar with them that you generally memorize them. It will make your life a lot easier throughout organic chemistry. Well, we've talked about what a positive charge does to the atom. It makes it more acidic, more willing to give up its proton because it would rather be neutral. Well, what about if it had a negative charge on it? So a negative charge does the opposite. Negative charge on the atom connected to the proton will decrease acidity. So as it gains negative charge, it is less and less likely to donate its proton. And we see that happening here. So here are the pKa values for this species. So it's losing a proton. Every time it loses a proton, it gains more negative charge, and the pKa rises. So this higher pKa is less acidic. It is more basic. So this species would rather gain a proton than lose a proton. Next up, we have the polar effect. So the polar effect is an effect which is not, so we're not talking about the atom to which the acidic hydrogen is directly attached anymore. We are talking about another atom in the molecule. So the polar effect comes from having an electronegative atom on the molecule which is not bonded to that acidic proton. And we see that an electronegative atom that's close to the acidic proton and the atom bond, remember this A stands for atom, it could be anything, it increases the acidity of the compound. So if there is an electronegative atom somewhere in the molecule close by to the bond that is attaching that acidic hydrogen, it's going to be affecting the compound or the acidity of that hydrogen. So let's take a look at an example. Okay, so here we have two different molecules. Well, let's talk about what makes them different. So the first thing that you need to be able to do is look at these and decide which of the hydrogens on it, because there's quite a few of them, which one is the acidic hydrogen that will be abstracted. So that's going to be, the hydrogen that's most easy to pull off is going to be on that directly attached to the more electronegative element. So here we have a hydrogen attached to this is a carbon, remember. So we have hydrogen attached to a carbon and we have a hydrogen attached to oxygen. Well, the hydrogen attached to the oxygen is going to be more easily abstracted than these. This is going to be the acidic hydrogen. Same here. So we're comparing a very similar molecule here, except for the fact that instead of having 3 hydrogens on this carbon, there's a chlorine. So chlorine is an electronegative element, and it's going to induce the polar effect on this molecule, and this one will not have it. So here we can, this is just proving to you that this one is more acidic than this one, but why? Well, it's because of the polar effect, and this chlorine is doing that. So what it's doing is taking electron density away this way, and these electronegative elements are also taking electron density away. So why is that important? Well, remember that a strong acid is an acid that has a conjugate base which is stable. So what does that mean? Well, once this acid does its acid thing and donates its proton, it becomes its conjugate base. So ignore this proton here. So think about it without the proton. It is its conjugate base, and so we have an electronegative charge here on this oxygen. Well, if the same thing were to happen to this molecule and there was an electronegative charge, this molecule couldn't really help very much with distributing the electronegative charge around. It would be pretty much centered over in this area. But on this molecule, we can see more sharing of the electronegative charge, a delocalization of the negative charge here is being helped out by the electron density pulling from the chlorine. So the electron withdrawing effect of the chlorine polarizes that CCl bond, creating a partial positive charge, lowering the standard free energy of the conjugate base. So if we lower the standard free energy of the conjugate base, it's more stable. The stable base is the important part. A stable base will mean that the conjugate acid, was more acidic and a stronger acid. So here you can see this negative charge is being delocalized between these two oxygens. Well, it's being helped out by the fact that this chlorine is also pulling away electron density. So it's kind of sharing this electronegative charge around a larger area, and it just makes the molecule more stable. So just to quickly recap, so this polarization effect, it's important to look at the conjugate base of your acid. So remember we had a proton here, it was abstracted, and now we get this, the electrons that were in the bond with this oxygen and the hydrogen came back onto the oxygen, and it's shared here, which we'll talk about in a second, why that's being shared. So don't freak out that you see this dotted line here. Just imagine that the electronegative charge here is just being delocalized between these two oxygens. So this negative charge is being balanced out by the electronegative element up here, and that's due to the polarization effect. So we can also talk about the resonance effect. And the resonance effect can be determined by looking at resonance structures of the conjugate base, which we just saw one. So we'll talk about that specifically. So here is a carboxylic acid. Again, make sure that you know all your functional groups here. If we said carboxylic acid, make sure you know what that would mean. But so here is a carboxylic acid that has its proton already been, it's already been abstracted. So there was a proton here, and it was taken off by a base. It is donated its proton already. And so now we're looking at this acid, this carboxylic acid's conjugate base. And just really quickly, be familiar with this whole design here. It's showing resonance. And so resonance will always be depicted by brackets and a double-headed arrow. And what is it showing? Well, it's showing where the pi electrons and where the negative charge can be on this molecule. So it's showing delocalization of this negative charge. So it's showing that it's delocalized, that it's moving around, and that's why it makes a more stable base. And we show where it could possibly be with our resonance form. So it could be that the electronegative charge is here and the pi bond is here, or the pi bond could come over here. And the electronegative charge then would be on this atom here. So we can show that by the hybrid model here, that we're just showing that there is delocalization between these two oxygens. So just really quick recap. This is resonance. This is how you show resonance. The resonance effect, if you see it in its a conjugate base of an acid, you will need to think, okay, well, that is stabilizing the base. So if it has that resonance stabilization, then the acid's going to be stronger because of it. And what's happening here, we have the square brackets, the double-headed arrow, these electrons on this oxygen. Think about how this would have 1, 2, 3 pairs of electrons and that negative charge. It can lay down those electrons into a pi bond, and then subsequently this pi bond electrons would pop back up here to the oxygen. So maybe think about how to do that on your own, and kind of explain that to yourself, because it's a good thing to be familiar with. Weak base, strong acid. A weak base is less reactive than a strong base, and a base that is less reactive is going to be a base that is more stable.